Dear engineers, welcome to VEDA Gate Academy and welcome to the world of opportunities. The topic here is K-maps, in which the subtitle Prime Implicants, Prime and Essential Prime Implicants, and it is also called as Initial to Essential Possibilities of a Boolean Function. The most important topic in K-maps and most logical even, which has very good questions in the competitive examinations, and you need to focus learning in a better manner. And I will also just try to teach you on a slow path so that you can also you will all be able to sync with the topic in learning. Yeah, let's go with. The topic is initial to essential possibilities of a Boolean function. Initial to essential possibilities of a Boolean function. And you know well, n variable Boolean function starts with product and sum combinations. N variable Boolean function starts with product and sum combinations. So, the first level of Boolean function is three power n minus 1 products or 3 power n minus 1 sums, which we already learned in the very first step. And from here, let it go. Two power n standard products, 2 power n standard sums. Standard products you call them as min terms, right? Mins. Standard sums you call them as max terms. So 2 power n standard products are 2 power n standard sums. And third level of the Boolean function goes to two power n declared min slash max terms. Repeat, 2 power n declared min or max terms. And this is called as coverages. 2 power n declared min or max terms. For a particular function, we will declare some min terms and some max terms and combinations. That is called as, so, coverages, I can say. Next, after coverages, we have implicants. The definition of the word implicant is C, coverage, which can be minimized. I repeat, coverage which can be minimized is called as implicant. After implicant, in digital, what we have is prime implicants. Prime implicants. The definition of the word prime implicant is, it is I implicant which cannot be minimized. I repeat, I which cannot be minimized. Don't you have an ambiguity between these two? Here he is telling implicant is coverage which can be minimized. Prime implicant is implicant which cannot be minimized. That means it is already once minimized. It cannot be minimized again. That's the meaning. So I should add a word. It cannot be minimized further. Cannot be minimized further. The very immediate and the final step of Boolean function is essential prime implicants. EPS, essential prime implicants. The definition of that is unique prime implicants. What do you call it as? Unique prime implicants. Hope you're clear with this sequence. So very first it starts with 3 power n minus 1 products or 3 power n minus 1 sums, and then with the min terms and max terms, then with the declared coverages, and then with the implicants, prime implicants, E prime implicants. And let me explain this topic in a detailed way with the best examples taken one by one. Sorry. I'm here with example 1. F of AB function product of some combinations. Can you just define them? Quick revision. Products A bar, B bar, A bar, B, AB bar, AB, right? A into 1, B into 1, A bar into 1, B bar into 1. Sums A plus B, A plus B bar, A bar plus B, A bar plus B bar, A plus 0, B plus 0, A bar plus 0, B bar plus 0. How many are there? 8. Here also 8. Formula 3 power n minus 1. So n equal to 2 variable, 3 square minus 1, 8. And I have an example 2. F of ABC. Oh, sorry, let us use the same term, AB. F of AB. Min or max terms? F of AB min slash max. So how many are there? 2 to the power of n, right? So 4. Min, max. So standard terms, right? Indicate standard. Hope you remember. So what are the standard terms here? A bar, B bar, A bar, B, AB, AB bar. That's all. Here max terms. A plus B, A plus B bar, A bar plus B, A bar plus B bar. So example 1 is product or sums. Example 2 is min or max terms. Example 3 coverages. And I even wish to take implicants together. Coverages and implicants. Map 1, map 2. So here is ABC, here also ABC. And I have the functions like this. Yes. So how would you declare the coverage and implicance in these both? So in this particular one, what is the definition of implicant? Minimized coverage. But in this map, no minimization. Not even a single square has a pair. Check it out. Not even a single square has a pair. So no minimization. So in this particular example, coverages are 4 minterms and implicants are 0. No minimization, right? Yes, it is. No minimization. Yeah. So in this example, how many are the coverages? 4 plus 3, 7. 7 minterms. How many are the implicants? Guess. When I give this question to the students, many of the students have answered. Implicants in this are, say, 3. Some people said. And some people said 2. Some people said 4 plus 3, 7. So 3 or 2 or 7. How many are the implicants in this? Implicants in the sense coverage which can be minimized. Everyone has a minimization, no? At least a pair minimum. Anyhow, the right answer of implicants from this example is definitely neither 3, nor 2, nor 7. As your friends were guessing, the answer is 12. 12 implicants. Now, you see in this map, how many pairs are possible? 1, 2, 3. And left and right, 4, 5, 6, 7, 8, 9. See here, 1, 2, 3, left and right, 4, 5, 6, 7. Where 9 are there, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many pairs? 9 pairs. And 3 quads are, however, there. Exactly. So 9 pairs and 3 quads, which is equivalent to 12. Now, can I change my definition for implicant? Can I say implicant is every possible minimization? We can, right? So coverage which can be minimized or every possible minimization. All pairs, all quads and all octets. So I'm just here making implicant is every possible minimization. Every possible minimization. Now, let me give you the next example to go with prime and E-prime implicants. Let me take in the next slide. So one more example will go with implicants. So third table. ABC. Yeah. So how many are the implicants in this? Just try to guess. How many are the coverages? Coverages are 3, 6. 6 minterms. Implicants. One, 2, 3, 4, 5. You see the pairs? 1, 2, 3, 4, 5. So 5 pairs. Do we have any quads? No quads. So implicants are 5 pairs. Now let us see prime implicants E prime implicants in a detailed example. Example number 4, I wish you day. For f of a, b, c, d. Here is my map. A, B, C, D. C bar, D bar. C bar, D, C, D, C, D bar. A bar, B bar. A bar, B, A, B, A, B bar. According to the gray map, gray numbers we have filled. Now the map is like this. Now, let us find out coverages, implicants, prime implicants from this map. And as we can declare, coverages are 13 minterms. How many? 13 minterms. And implicants, students, funny thing here, this question I have raised almost with lakhs of students out of my 15 to 20 years experience. But very rarely I got the answer for this. Very rarely. Say about ones in thousands. Just counting implicants from this map. Try to. May you just start counting and work out on. But some way or the other you'll make a mistake. Can I tell you the simplest way, easiest way to count the implicants? In a sequence. First go horizontal, then vertical. Other way vertical or horizontal, whatever the way you want. But not zigzag. Just try to go in a sequence. I'm just going horizontal counting pace. 1, 2, 3, left and right, 4. Left and right, 5, 6. Here no one. 7, 8, 9, left and right, 10. So horizontally 10. Vertically 1, up and down 2. Top and bottom 3, 4. Top and bottom 5, 6, 7, 8, 9. Top and bottom 10. So vertically also 10. So horizontally 10 pairs, vertically also 10 pairs. Totally how many pairs we got? 20 pairs. Plus, can you count the quads? You can. Top 1, 1, no one, no one, 2. Horizontally 1 and 2. Next top and bottom 3, 4, 5. Top and bottom 3, 4, 5. 6 here, 7 here, left and right 8 here, 4 corners 9 here. I repeat once again, 1, 2, 3, 4, 5, 6, 7, 8, 4 corners 9. So 9 quads plus 1 octet. Where is octet? The top and bottom, the octet. So let us see the coverage. Yeah. This is an octet. Here is a quad. Here is a quad. Here is also a quad. Left and right. And here is a pair. Yes. 1, 2, 3 quads. And this pair and up and down octet. Yeah. Now let me count prime implicants. From this function, how many are the prime implicants? You see 20 pairs are there. Except this pair, all the other pairs are in quads. Except this pair, all the other pairs are in quads. So let us not count the others, only this pair. So prime implicants, only one pair, plus how many quads are prime implicants? How many quads are not in octet? That we have to count. And this is how the octet top and bottom. So this quad is already in octet. Second, this quad is also already in octet. This is in octet. This in octet. This also in octet. 5. And 4 corners are also in octet. 6. I repeat. The top one in octet. This down one in octet. This one, this one, this one also in octet. 5. And 4 corners. 6 quads in octet. They are not prime implicants. Then which are the prime implicants? This 4 is not a part of 8. This 4 is not a part of 8. This left and right is not a part of 8. I can take them into quads. Sorry, prime implicants. So 3 quads. Anyhow, 1 octet is a prime implicant because it is definitely not in 16. It is only 8. So number of prime implicants are 5. Number of implicants are 30. And number of essential prime implicants, E prime implicants. What is the meaning of E prime implicants, which I already told you? Unique prime implicants. Now let us see what do you mean by the uniqueness. Yeah. Here, in this pair, for this square, I can take a pair like this, I can take a pair like this, I can take a pair like this. But for this square, this is only the pair possible. Correct? So, this is unique in this. Next, in the square, so only one pair is prime implicant. That is, however, unique. So, one pair. Plus quads. In this quad, for this square, I can also take like this. For this square, I can also take like this. For this square, I can also take like this. And the square which has no option except only this quad is this. So because of this, this is unique. Because of this, this is unique. Next, this one. I can have the a quad like this, I can have a quad like this, I can have a quad like this. These 3 has other options except this. Correct? This doesn't have another option. So this is unique here. Because of this, this complete quad is unique. Similarly, the left and right one, this is not unique, this is not unique, this is not unique, this is unique. So how many quads are unique? 1, 2, 3. So all the 3 prime implicant quads are unique. So 3 quads. Plus 1 octet is however unique because there is no hex at all. There is no other octet also. So every square in octet is unique. All these 4 and all these 4, the possibility, the highest possibility is only octet. Now, come back to speak output. Function y is equal to the top and bottom, the octet, b bar, plus this one, cd bar, quad, this quad, a bar c, and left and right quad, a bar d bar, and a vertical pair here, a c bar d. Students, I want you to declare in this map which one is unique because of whom, essential because of whom, which square. So EPI, essential prime implicant because of, yeah, B bar is essential prime implicant because of, B bar is essential prime implicant because of all these 4, all these 4, 8 are essential. So all terms in it because of, all terms in it are essential. CD bar is essential because of this square, 12, 13, 14, 15. So M14. CD bar is essential because of min term 14. A bar C, here A bar C, this one, this square. So 4, 5, 6, 7. So because of min term 7, it is essential. And A bar D bar, left and right, this corner M4, min term 4, it is essential. And this pair is this one. So 12, 13 because of M13. Now I hope you have a complete idea how to pick essential prime implicants, either by one square or multiple squares. It can be essential, for which only that possibility, there is no other possibility. Done. The way to pick implicants, prime implicants and essential prime implicants, I repeat, product or sums later, min or max terms later, declaration coverages later, minimization 3-level, implicant, prime implicant, E prime implicant. Implicant is every possible minimization or the declaration which can be minimized. Prime implicant is implicant which cannot be minimized. Essential prime implicant is so unique prime implicant. Now, in this case, I just wish to take a short note on prime implicants. Once again, here, frame prime implicant when. One particular frame, when is it a prime implicant? 2 power 1 adjacency. That is called as a pair, right? Pair is a prime implicant when not in 2 square adjacency. 2 square is quad, right? So pair not in quad is a prime implicant. See, if a pair is in quad, we'll take quad. Why do we take pair? Correct, right? If a pair is in a quad, we'll take quad. Why do we take a pair? So then pair is not a prime implicant if it is in quad. So if it is not in quad, it is a prime implicant. Similarly, 2 square adjacency. So what is that? Quad. It is a prime implicant when not in octet. Octet is 2 cube adjacency. So 2 cube adjacency, octet. Octet is prime implicant when not in hex. What is hex? 2 power 4 adjacency. So similarly, 2 power n adjacency is a prime implicant when not in 2 power n plus 1 adjacency. You're clear, right? So pair not in quad not in octet, octet not in hex, 2 power n not in 2 power n plus 1 are the prime implicants. Hope you're clear with this example to solve many more one by one. Let me take example 4, example 5. F of ABCD a map here. ABCD. Yeah. From this map, try to figure out implicants, prime implicants, E prime implicants, and output declaration. If you want to declare the output, C bar, D bar, C bar, D, C, D, C, D bar, A bar, B bar, A bar, B, A, B, A, B bar. Right? So now let me tell you how many are the coverages. 2, 4, 7, 10 minterms. How many are the implicants? Implicants. No one, 1, 2, 3, 4. 1, 2, 3, 4 pairs. 5, 6, 7, 8, 9, 10. I hope 10 pairs. I repeat once again, no one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excellent. Quads, I hope it is a single quad. One quad. So totally 11 implicants. Single quad. I'm sorry, two quads. Ten pairs plus two quads. 12. Now come back to speak primes. PIs. How many quads unique? Anyhow, these quads are not unique. Only this quad, I think. All other quads, sorry, all other. How many pairs are unique? I'm sorry. This pair is unique. None other pairs. All these pairs are in the quads only. This pair, this pair, this pair, this pair, this pair, this pair, all in quads. So not necessary to count on. So this pair is unique. Anyhow, to speak. This quad and this quad are also unique because no octet, only quads are available, no other quads. This quad is unique and this quad is unique. Two quads and one pair. And anyhow, these are single terms, no? One not a part of two. Also called as a prime implicant, we already declared. So number of primes are one pair plus two quads plus 1, 2, 3, 1, 2, 1, 2, 1, 2. Here I just want to tell you one more pair possible. Yeah. Yeah. Just 1 second. 10 means, let me count once again. Small overlap. Yeah. Check it out. One more pair possible. Already pairs are 10 given, I think. Let us once again cross check. Implicants are here now 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And where else is 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 pairs. That's not an issue at all. Quads are also 2 quads. I'm talking about how many pairs are not in quads. That should be taken up. So unique pair combinations. So implicants are over. 10 plus 2. Prime implicants. 2 not a part of 4. This 2 not a part of 4. This 2 as a part of 4. This 2 as a part of 4. This 2 as a part of 4. This 2, all these 2 as a part of 4. Leave it. And this 2 not a part of 4. This 2 is not a part of 4. This 2 is also not a part of 4. So let me take this one and also this one and also this one. 3 pairs. Not in 4, not in 4, not in 4. Plus, how many quads? 2 quads are anyhow not in 8. Totally 5. So prime implicants are 5. There was a small confusion here. That is why I have explained once again. So now E prime implicants on the same topic. Try to find the uniqueness in this. Unique. Who is unique by whom? This quad is unique by this, can I say? For this term, this is only the way. This quad is unique by this, can I say? For this term, this is only the way. So 2 quads are unique. This pair is unique by this. This pair is unique by this. This pair is unique by this. And the single one is however unique. However unique. And prime implicants, anyhow, one more is there here. Single term. Plus 1. 2 quads plus 1 single term. 1 unminimized. E prime implicants. Both the quads are unique. How many pairs are unique? 3 pairs are unique. Plus 2 quads are unique. Plus 1 unminimized anyhow unique. 1 single square. Left. So finally here also 6. Yeah. Implicants are 12. Primes are 5 plus 1, 6. E primes are also 5 plus 1, 6. Can I say in this, all prime implicants are E prime implicants? And note, all PIs are EPIs. All prime implicants are essential prime implicants. So in this example, and else to go, let me take example 6. Yeah. Example 6 I wish to. F of ABCD. And this is my map. Yeah. Check out. C bar, D bar, C bar, D, CD, CD bar. A bar, B bar, A bar, B, AB, AB bar. A map is like this. Yes, and this is how the map is. From this, let us find the implicants, primes and E primes. Our first coverages 4, 5, 6 are minus 10 coverages. So 10 means 3, 7, 10. Implicants 1, 2, 3, 4, 5, 6, 7, 8, 8 here, 9, 10 and 11, 12, 13, 14. I repeat once again. 1, 2, 3, 4, 5, left and right 6, 7, 8, sorry, 9, 10, 11, 12, 13, 14. So 14 pairs. Plus how many quads? 1, 2, 3, 4, 5. 5 quads and no octet. So 19 implicants. Correct? And just mark it. One, 2, 3, 4, 5. And let me find prime implicants. 2 not a part of 4. 2 not a part of 4. 0. All the pairs are in 4 only. Every pair is in 4 here. Because only quads, no pairs, no octets. All the 5 quads are primes. Because no octet. Quad is a quad only. It has no other minimization. There is no pair at all. So 0 pairs are prime implicants. All the quads are existed but no octets. So all the 5 quads are prime implicants. So totally 5. Prime implicants are 5. In this E prime implicants, just try to note down the uniqueness here. This quad is unique by him. And this quad is unique by him. This quad is unique by him. And this quad is unique by him. So 4 are unique. Center quad is PI but not EPI. Check out. But not EPI because no unique term. No uniqueness. Every one is a part of others. Because no unique terms. Hope you understood what is the meaning of PI, not EPI. Are you clear? So, this is the best example to understand. It is only a prime but not E prime. Example 7. I just wish to give you one important note. Maybe after this, example 7, we have a map like this. We do have a map like this. Sorry. Yeah, the maps are given like this. We have a question. Maps are known as. There is one special name for these maps, and he's asking you what is that name. Maps are known as. Let's understand the pulse of the maps here now. Can I say every coverage is implicant? Every coverage, minimum a pair is there. Minimum a pair. At least a pair for everyone. So, every coverage is implicant. That's what statement number 1. Statement number 2. Can I say every implicant is a prime implicant? And only pairs in the whole 2 maps. Only pairs, no quads. So, 2 but not 4. Every pair is only a 2, not 4. So, it is a prime implicant. Only pair, not quad. Sorry. Every implicant is a prime implicant. Statement number 3. But no PI is EPI. I repeat, but no PI is EPI. Is it correct? Yes. Everywhere, all pairs possibilities are there, but no unique pair. Not even a single pair is unique in these 2 maps. Check it out. Not even a single pair. For this, I can take like this or I can take like this. For this way or this way. 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 For every one, we have two options. You can check out. For this also, you can go like this or like this. For every square, we have two options. In this map also, we can take like this, or you can see in the other way. One, 1, 1, 1. The other way how you can check is, yeah, like this. So for every pair, there is the other option. For every square, there is the other option. No uniqueness. None of them are unique. So I repeat, every coverage is implicant. Every min-term is implicant. Every implicant is a prime implicant. But no prime implicant is essential prime implicants. No essential prime implicants. These kinds of maps are known as, a very important statement. Cyclic prime implicant K-map. I repeat, cyclic prime implicant K-map. Prime implicants are cyclic. Hope you're clear. And most important competitive question. Then, let me explain. Example 6 is done, right? Cyclic. Example 7 is also done. Cyclic prime implicants K-maps. Example 8. Yeah. The terms familiar or you know well. Product or sum. Then min or max. So let's do like this. Product or sum, min or max, coverage, implicant, prime implicant, E prime implicant. This is how the chain we learn, right? Yeah, what is the link? So, product will be min, sum will be max. Both together, coverage. Coverage after, implicant. Implicant after, prime. Prime after, E prime. The sequence and rule is E prime must be prime. Prime must be implicant. Implicant must be the coverage. Coverage must be the min or max. Min or max must be the product or sum. That's what known to you, right? But here one thing. Implicant is prime, but every prime is not implicant. Sorry. E prime implicant must be prime, but every prime need not to be E prime. So which is E prime? Unique prime is E prime. What is this? Not all primes. Unique prime implicant. Prime implicant is an implicant, but not every implicant is a prime implicant. Which implicant is a prime implicant? Implicant with no further elimination or minimization. Correct? Implicant is a coverage, but every coverage is not implicant. So which coverage is implicant? Coverage, or I can say minimized coverage. Minimized coverage is implicant. Coverage must be min or max, but every min or max is not coverage. Which min or max is coverage? Declared. Only declared min or max term is coverage. Min must be a product and max must be a sum, but every product and sum need not to be the min or max. Then how? Standard product is min, standard sum is max. The condition is this. But in one example, this one, I can say coverage will become a direct prime on E prime without falling an implicant stage. Yes, coverage will be direct prime and implicant. This will be prime and this will also be E prime without falling an implicant stage. Without falling on implicant stage. Can you just guess the example for that? Yes, you can. Yes, please. Can you just guess from this map? Say coverages are 4, implicants are no minimization, as I have already explained. No minimization, not even a single square minimized, 0. Primes 4, E primes are also 4. How come primes and E primes are 4 when implicants are 0? Because prime must be implicant and E prime must be prime implicant? Yes. The link here is, how did they become primes bole to? The statement is, it is only 1 square, but not in 2. As we told you, 2 not in 4, 4 not in 8, 8 not in 16. Pair but not quad, quad not but octet, octet but not hex, like that. Single square but not in 2 is also a prime implicant. Similarly, essential prime implicant, unique on its own. The term is unique on its own. The most important topic is this. So, everyone is unique on its own. You cannot minimize it. You have to essentially write down. So, finally, output declaration of a Boolean function after a map simplification is that first unique minimizations, then unminimized terms are also the parts of the output, which you need to understand. Unique minimization plus unminimized terms. Both are called as essential prime implicants. I hope you're clear with this example very much. Thank you. After this, the most of the important terms are covered. We'll just take one example on the last example to solve all. Here is a map. A, B, C, D. Here my terms are like this. Yeah, this is my map. And let me find implicants, prime implicants, essential prime implicants. How many are the coverages? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many are the implicants? No pairs here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. Here 7, 8, 9, 10. Are we correct? Check once again. Here no one. 1, 2, 3, 4, 5 and 6 vertical. 7, 8, 9. Here no one. 10. So 10 pairs. Do we have any quads? Yes. We have 2 quads. 3 quads in fact. 2. Also this. Yes. 3 quads. Yeah, which I've already drawn. One single square is left. Anyhow, unique on its own. I told you, right? Single square left unminimized is also unique. E prime implicants. So prime implicants, 0 pairs. So all the pairs are in quads. Plus 1, 2, 3. 1, 2, 3 quads. Octets are not there anyhow. So E prime implicants. Try to identify the uniqueness here. This quad, these both are unique. This quad, this can be this way. This can be this way. For this, there is no other option. This is unique. Left and right quads, this has other option, this has other options. These two have no other options. Unique because of these two. That single square is anyhow unique on its own. So E primes are all the 3 quads. Plus 1 single square. 1 unminimized term. UMT, unminimized term. So come back to speak. Y output equal to C bar D bar. Sorry. A bar B bar. A bar B. A B bar. Y equal to AB1 quad plus left and right is AD bar plus the center quad is BC bar plus single square left is A bar B bar CD. So who is unique by whom? EPI because of, yeah, quick. AB is UPI, EPI, I'm sorry, AB is EPI, 12, 13, 14, 15, M15. This is unique because of 4, 5 both. M4, M5. Min-term 4, 5. These two. AD bar. Oh, sorry, here we just. AD bar is this, right? So, left and right, AD bar. AD bar is because of 8, 9, 10, 11, 8, 10. Min-term 8, min-term 10. BC bar. BC bar, that left one. So, BC bar is unique because of 4, 5. M4, M5. A bar, this square is 0, 1, 2, 3 on its own, right? Min-term 3. M3. Now I hope you'll be able to solve any question based on prime implicants and E-prime implicants. Rehash, product term sums, standard product term sums to become min or max terms, and then declared min or max terms to become coverages, and minimized coverage is implicant, every possible minimization. Implicant which cannot be minimized again, only once minimized, 2 not a part of 4, 4 not a part of 8, 8 not part of 16, prime implicant, and prime which is unique, E-prime implicant. Done. Single squares which are unminimized are also E-prime implicants. The most important topic of this. And later after, from quiz 1, I have some more focused questions which I feel you need the help of it to solve. Let me solve them one by one. From a quiz 1 of the basics topic, number systems and data formats, I have some questions to help you in giving your solutions. Yeah. Quiz 1, the questions given are this, and some of them I picked out to give you the solutions for you. 4-bit number x3, x2, x1, x0 stored in 8-bit form is, if I store a 4-bit number in 8-bit form, how it looks? That's the question. My 4-bit number is this. LSB is x0, MSB is x3. Correct? So, if I just give you the question here is x3, x2, x1, x0. That's the question. But I want to store this in 8-bit form. When storage is extended, the question, when storage is extended, do I need to extend least or extend most? Question 1. On least extending, most extending with zeros or the same bit? Question 2. So, 2 logics are here. First logic is, do I need to extend least or extend most? Second logic is, extend with the same or zeros. When this fundamental comes, storage extension is always done by sign extension. So, the fundamental base is storage extension is done by sign extension. Storage extension is done by sign extension. So, sign is x3, right? MSB, most significant bit. So, any number of bits extending with a sign is what storage extension. So, he is asking 8-bit now. So, x3, 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 x3. The original data is 4-bit data. x3, x2, x1, x0. So, which is sign extension now? And this is sign extension, this is sign. And this is sign extension. Finally, storage extension is possible by sign extension, which is the right answer. Where the sign is extended here. This is sign. So, C the right answer for the question. You're clear, right? So, the next question is, signed 2's complement form of minus 589 in hexadecimal. Minus 589, first you convert into binary, then into hex, and then into 2's complement form. I'm sorry. Yeah. Minus 589, the data. binary format is begin from 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, right? So begin with the 512. 512 must be 1. Minus 589, no? So sign also must be 1. Negative. 512 after 256 must be 0. You don't use it. How much more is required after 512? I think 89, no? So 77 more is required, no? 512 after, to get 589, 77 more is required. So 256 absent, 128 absent, 64 present, 77 more. 64 हो गई तो 77, 13 more, no? So 64, 32 not required. So how much is it? 64 and 77, 13 more. After that, 512, 256, 128, 64, 32 absent, 16 also absent, 13 is 8421, 1101. I hope your binary answer is ready. Check out once again. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. 512 after 589. So 77 more. 77 is 64 plus 13, 77. So 589 is done, complete. Now 2's complement. This complete data is 589. I already taught you in the first class itself, without doing a division, how to convert the number shorter way to binary value. And 2's complement. Anyhow, sign should not be complemented, remain the same. 2's complement for the data. Sign must remain as same. Data 2's complementing. 0, 1, 1, 0, 1, 1, 0, 0, 1, 0 plus 1. And this is 2's complement. 0, 1, 1, 0, 1, 1, 0, 0, 1, 0 plus 1 is 1. Yeah. Now we have to convert this into hexadecimal. Hexadecimal is in the form of a 4-bit, no? Distribute into 4-bit. 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 Here 1 bit is less. Only 3 bits are there. I have to extend. Whenever I extend the data, you need to extend the sign bit. Remember, this is sign extension. In the previous example, I have already explained. So then what is the data? 1101D, 1011B, 00113, DB3 right answer. Yay! Here is the right answer. I hope it is logical. See, converting this is simple. Till here, there is no issue at all. Extension of sign is very important to know. Otherwise, if we make 0 here, it will be 5B3. See, 5B3 is also there to confuse you. So take care of that. Here we have number of ones present in 11, 256, 13, 16 plus 14. Some multiplication addition number based in converting into binary. We want to get number of ones available in that. There are 2 ways. If you go mathematical, just simply multiply and add, you get decimal, convert into binary, you will get the answer, but that is lengthy. I don't want you to go in that way. Simply multiply, add, and decimal number convert into binary is a waste of time. There is a logic here. Try to guess. That is, here I mean 11, 13, 14. Can I write like this? Into 256, into 16, into 1, can I? Yeah, I can. Next step. 256 is 16 square. And this is 16 power 1. 1 can be 16 power 0. I can write like this. Now, don't you think 16 power 0, 16 power 1, 16 square is a hex number? hex number. So why don't you write in that way? 11 hexadecimal is B, 13 hexadecimal is D, 14 hexadecimal is E. So B, D, E hexadecimal it is. B, D, E hexadecimal. Now what is B, D, E expansion? B is 1011, D is 1101, E is 1110. Now see how many ones are there? Over. The simplest way to go. So count number of ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 ones are there. If you go in mathematical way, it's lengthy and as well as waste of time. Shorter way, try to guess some logic will be involved in that. Maybe octal number, maybe hex number, maybe your nibble number, whatever. Try to find out. Next. Number of ones in 8-bit form of minus 127. In 2's complement form is m. And in 1's complement form is n. M is to n is. So firstly, minus 127. We have to write in 1's complement and 2's complement. Write on that. Minus 127. Yeah. First write in binary form. Sign bit is 1, no? Then remaining. $127 in the sense, all ones, I think, isn't it? 128 beyond one of all ones, 121. 1, 1, 1, 1, 1, 1, 1, 2, 4, 8, 16, 32, 64. Altogether it is 127. You can count it. So, this is binary. But we want in 2's complement form. Sorry. 2's complement. First 1's complement, then 2's complement. Negative. 1's complement answer is 0, 0, 0, 0, 0, 0, 0. This is signed magnitude. This is 1's complement form. This is 2's complement form. Next 2's complementing. Sign is as it is. Complement of the data. 0, 0, 0, 0, 4 zeros. 0, 0, 1. 1's complement plus 1, no? Now his question is, and this is n, this is m. What is m is to n ratio? So number of ones in 2's complement are m. Here how many ones are there? 2 ones. What is it stating as m? How many ones are here in this data? Single one is stating as n. So what is m is to n? Here. 2 is to 1, right? Simple. Here 2 ones are there. Here single one is there. That is how he wanted. Here 2 ones are there. And here single one is there. So number of ones in minus 127, 2's complement form are 2. Number of ones in minus 127, 1's complement form is 1. So 2 is to 1. The right answer, where is that? C. Yeah. Hope you're clear. Sometimes, looking into the question, it may make you to feel lengthy, but you could do it faster. Next. Yeah. 2's complement numbers with xy as a sign bits are added. Got resultant sign z. The occurrence of overflow here is indicated by. Occurrence of overflow here is indicated by. In digital, in this term particular, overflow is called as sign error. I repeat, it is a sign error. Overflow means not carry, it is a sign error, especially in 2's complement operation. Overflow in 2's complement addition is called as overflow. 2's complete addition. Yeah, it is called a sign error. So whenever you add numbers, when there is a chance of a sign error, you add two positives, number must be positive. You add two negatives, number must be negative. So adding two positives, you're getting negative. Adding two negatives, you're getting positive. That is an error, right? Anyhow, adding 1 plus 1 minus, error will not occur. It depends on. Only when you add two positive numbers, only where you add two negative numbers, then only the error will occur, right? Now, when you look into, so sign error may occur yet. Say x, y, z. So x sign is positive, y sign is positive, z must be positive. Because you're making an addition between them. No, z is x plus y, we told you. And then x sign is negative, y sign is negative, z must be negative. Are we clear? So can we extend this? X, y, z. So x is 0. That means positive number. Y is also 0. That means positive number. Z is a resultant sign. Yeah, must be 0, right? As I told you already. That means positive. Repeat the next line. X is 1, negative number. Y is 1, negative number. Z must be. Resultant sign must be negative. If it is not that, then it is error. He is asking you equation for error. What is correct equation first? Correct equation first. X0, Y0, Z must be 0. So, X bar, Y bar, Z bar is correct. Plus X, Y, Z, 1, 1, it will be 1. X, Y, Z, correct. If these both are zeros, this must be 0. If these both are 1, this must be 1. That is why the operation showing. Min terms, right? 0, 0, 0, 1, 1, 1. So if X is 0, Y is 0, Z must be 0. X is 1, Y is 1, Z must be 1. So correct equation is X bar, Y bar, Z bar plus X, Y, Z. The wrong equation is, or you can say error is, or you can say overflow is, equation for overflow. If these are 0, it is 1 coming. That is wrong. So X is 0, X bar, Y 0, Y 0, Y bar, Z is 1. That is wrong. If they are positive, how it will be negative? Wrong. Similarly, X is 1, Y is 1, Z is 0. This is the wrong equation. So sign error is both zeros, positive numbers, but negative answer. Both negative, but positive answer. That is how the error occurs shown. Positive inputs, negative result. Similarly, negative inputs, positive result. That is error. Anyhow, equation which is matching for this is, where is that? X bar, Y bar, Z plus X, Y, Z bar. Yes, C. And you can take examples for this and solve it. You can take, A greater than B example of A minus B, A less than B example of A minus B. Different examples taken, come to a universal conclusion, and you'll get to the same. You can try with examples. We don't mind. Take two positive numbers along with sign, make a 2's complement addition. Take two negative numbers along with a sign, make 2's complement addition. This will be followed. Anyhow, universal formula is adding two positive numbers, result must be positive. Adding two negative numbers, result must be negative. If it is not coming, it is an error, overflow, occurrence of overflow. I hope you're clear with this. 1, 2, 3 base 5, x8 base 5. Number of possible solutions when xy are unknown. 1, 2, 3 base 5, x8 base 5, the number of possible solutions when xy are unknown. Yeah. Let me take the number. Sorry. Mm, 5 square, 2 into 5, 10, 3 into 3 power 0. 5 square is 25, 2 5s are 10, plus 3 is equal to xy plus 8. So xy plus 8 equal to 38. Xy plus 8 equal to 38. So xy equal to 30. Xy equal to 30, how many possibilities are there? X into y is equal to 30. Can I say different options? 1 into 30, 2 into 15, 3 into 10, 5 into 6, 6 into 5. So 1 into 30, 2 into 15, 3 into 10, 5 into 6, 6 into 5. So totally 5 options for xy. For x also 5 possibilities, y also 5 possibilities. Answer A, 5 comma 5, which is very clear. And this is how the question is confusing you. The inner logic you did not guess. 5 comma 5 is wrong. And let me tell you what is right answer. In this, you are trying to understand one thing. x8 base y. In a base y number, x is a digit. In a base y number, x is a digit. I told you already, for any base number, the digit must be less than the base, or the base must be greater than the digit. I repeat, the digit must be less than the base, or the base must be greater than the digit. In that case, if y is a base, so x must be less than y, and y must be greater than 8. 8 is already declared, no? It must be definitely greater than x and greater than 8, both. So x must be less than y must be greater than 8. 3 into 10, also greater than 8. In all these 3 cases, didn't we make 3 into 10? Yes, we did. 1 into 3, 2 into 15. Yeah, these 2 possibilities are failed. 5 into 6 and 6 into 5. So here 1 into 30, 2 into 5, 3 into 15, 3 into 10. In these 3 cases, it is, y greater than 8. So x must be less than y. Anyhow, that is also followed. So this condition is there very much. So only 3 combinations are allowed. So 3 comma 3. Clear? You see the logic in this. By a basic way, we take with this. But if in detail we went on, the answer is 3 comma 3. And next we have the question. The number of distinct 16-bit integers in 2's complement or y in signed magnitude x, then x minus y. X the number of distinguished 16-bit integers in 2's complement, y in signed magnitude, then x minus y. Yeah. And here the solution. Than 16-bit integers. Let us take 4-bit example, because he's asking the difference, no? It is same either between 4-bit or 16-bit. Than 16-bit, let us take 4-bit example. Four-bit 2's complement range. 4-bit 2's complement range. -8 to -7 to -1, comma +0 to +7. How many are the possibilities? minus 8 to minus 7 minus 1 plus 0 to plus 7. How many are the possibilities? 15, 15, 16, no? Yes. And 1's complement, sign magnitude, I'm sorry. 4-bit S magnitude range. I'm sorry. Minus 7 to minus 0, comma plus 0 to plus 7. How many here? Here also minus 7 to minus 0 plus 0 plus 7. The values are 16 only. Excellent. So what is x, what is y? And this is x. And this is y. What is asking x minus y? 16 minus 16, 0. Do we have answer? Yes, we have. This is the way where majority of the people will solve and will go wrong. A is wrong answer. A is wrong answer. Let me explain why. Come back to speak. Here he is asking you very particularly integers. Please look into it. Integers. And here minus 0 is not an integer. Then if you remove minus 0, what is that? It is 15 only. So then 16 minus 15. What is the answer? 1. Great. This is the logic of the questions in GATE examination. Looking to be very simple and silly, but every question will have some way the other way logic involved. Except 10 to 15% of questions are straight, remaining all logical based, computative based, analyzation based. And next. Yeah. Square root of 144 base r plus 2 are equal to. Yeah. Less than or equal to 4, greater than or equal to 4, equal to 4, none. Let's see how do we solve this. Remove square root and get this side. Remove square root, get this side. Apply r here. R square plus 4r plus 4 is equal to a plus b whole square in the form of a plus b whole square. R square plus a square plus b square 4 2ab 4r. Same story. LHS equal to RHS. So R must be greater than 4. If R is the base, inner the number must be greater than 4. If R is if the number in base R is 4, I'm sorry, for 144 if base is R, so the R must be greater than 4. So we told you already, no? The number must be less than the base must be greater than the number. The number must be less than the base must be greater than the number. In that case, R must be greater than 4. Where is that? None. You're clear, right? So base must be greater than the number. Number must be less than the base, which I already explained. Base must be greater than number. Or I can say digit, not number. I should not say number. Or I can say digit must be less than base. Following this, and you solve this question. 67 base are 5, 1, 3 are equal to. So apply the base numbers. Take 5 that side. 6r plus 6 is equal to r plus 3 into 5. Take 5 that side. So 6r plus 6 is equal to 5r plus 15. So finally 6r, 5r, r equal to 9. Isn't it? Apply r equal to 9. Proof. 6 into 9 plus 6 equal to 5 into 9 plus 15. So 60 equal to 60. Exactly correct. Right. The last question for this topic to discuss. Data plus of all ones in binary equal in length is equal to. Data plus all ones in binary, these both are equal in length is equal to. Increment of data, decrement of data, data gets cleared, none of the above. Let's see what is the right answer. And here is, can I say data plus of all ones? Oh, I just wish to come from the answer. Yeah, I'm sorry. State the answer and then come. Answer is data minus 1. Decrement of data. I'll give you the proof how it is the data minus 1. So data minus 1, can I write it as data plus of minus 1? I can. Data plus of minus 1, can I go as plus of 2's complement of 1? Because minus 1 I can write 2's complement of 1. Minus 1 I can write it as 2's complement of 1. So data plus of, how do you represent 2's complement of 1? First minus all zeros, last 1 is what? Signed magnitude form first. And this is signed magnitude form. Make signed 1's complement form and then 2's complement form. Data plus of 1 remains the same. 1, 1, 1, 1, dash, dash, 1, 1, 0. What is this form? 1's complement form. Finally, 2's complement form. Data plus of 2's complement is adding one more. 1, 1, 1, 1, 1, 1, 1. This is 2's complement of minus 1. So 2's complement of 1 is this. The question is same, right? Data plus of all ones equal to data minus 1. Data plus all ones equal to data minus 1 because, go again in the reverse way to understand. So any data in binary, addition of all ones, it will be decremented by 1 because all ones will act as minus 1 into 2's complement form. All ones will act as minus 1 in 2's complement form. I'm here with an example. My data is 10110. What it is? 16 plus 6, 22 decimal. And I'm adding all ones to that. You see the result. 0 plus 1 is 1. 1 plus 1 is 0 with carry 1. 1, 1, 1 is 1 with carry 1. 1 plus 1 is 0 with carry 1. 1, 1, 1 is 1 with carry 1. Leave carry. Carry will not be in the magnitude. Take out this. Answer is 21. So 22 plus all ones equal to 21. 22 plus all ones in binary equal to 21. So like how you can make digital operations faster knowing this kind of smarter techniques. End of it, the topic basics are successfully completed. Number systems and data formats, logic gates, Boolean algebra, K-maps, prime implicants. And our responsibility of delivering a lecture is 50%, and your responsibility of practicing the topics and theory, practicing the questions, looking into the solutions, giving you the quiz questions, getting the quiz solutions, knowing through the discussions of the questions, and extra miles to read the other practice sessions. All this will make you getting the best step. So if you take 50% of role in this, regular to the class, listen perfectly and carefully, practice CRQ which is given behind, and going through CRQ solutions, and going through the material what has been given, and attending the quiz programs, and solving the quiz questions, going through the solutions of the quiz, and then whatever the system is given by the institution, the schedule, if you follow, the 50% of role is done. I'm sure even an average student, if they follow this system perfectly, he'll be able to score 50 plus marks. If you score 50 plus marks in the GATE exam, you are damn sure into the top institution for your MTech admission. Go beyond, 50 plus, and then you will be, raising your range for top IIT, top institutions, top courses, and masters into it. Government jobs, what you get on. So GATE is never tougher. Please don't say that. 10 subjects it has, it is tougher. No, no, never. Even if 10 subjects or 100 subjects are there, if I have a system, if I have a plan, if I have a strategical preparation, as I have already told you in preparation strategy, video, and things will be simple. Try to understand that. Nothing is impossible, especially digital, logical based subject, which you can definitely do the best on. All the best to you. Thank you.